Hello, afternoon students. So today we are going to cover the asymptotic notations in the data structures. So first of all, I will brief up the things that we are going to look into this presentation. So here we will list out the factors that affects efficiency of an algorithm. Then we will identify the techniques to measure the efficiency of an algorithm, and we will also understand the various asymptotic notations which are used to measure the efficiency of various algorithms. So here first we will start with the factors that affects the efficiency of a program. So in previous sessions we had already seen that if we need to write program, we first need to write algorithm for it, and the algorithm which provides better efficiency should be chosen to write the program. So here are the some factors that affects the efficiency of a program. The first one is the speed of a machine. The speed of a machine imposes various restrictions on writing a program as well as executing a program. So the speed as of now does not plays much more importance, because nowadays we all are having computers with better microprocessors i3, i5, i7 and all. So the speed of machine in general life does not plays a much important role in the efficiency. However, the second one, which is the compiler, plays a very important role, because it completely depends upon the type of compiler how the algorithm or the program will be executed. So for programming languages like C, C++, Java, C hash and Python, the compilers are of different types. Hence, the execution criteria, the execution time as well as the consumption of resources also differs in different programming languages. Hence, compiler plays a very vital role during the execution of a program. The next one is the operating system. The operating system also gives much efficiency in writing a program, that completely provides the UI, that is the user interface for a programmer to write their algorithms and convert or transform those algorithms into the respective programs. The next one is the programming language. As now we had discussed that the different programming languages like C, C++, Java and many more have different interfaces and different mechanisms of processing the instructions. Hence, it completely depends upon the user to select an appropriate programming language to write their program or to transform their algorithm into an executable one. And the last one is the size of input. The size of input completely signifies the amount of input supplied to the program when it is in execution. So higher the input rate, then the program will take more time to display the result or to formulate the output. Hence, these are the few factors which affects the efficiency of a program. We can minimize these, or we can have a better balance among all these factors to write a good program. In addition to these factors, the way data of a program is organized and the algorithm used to solve the problem also has a significant impact on the efficiency of a program. That is the data structure as well as the algorithm. Algorithm provides a basic grammatical solution to a given problem, whereas a data structure provides a mechanism which will physically implement those algorithmic steps into a program. We cannot execute an algorithm, but we can execute a program. Hence, it is very much important to select a better, rather a best data structure for our program. The efficiency of an algorithm can be computed by determining the amount of resources it consumes. The resources. When it comes to resources, we generally talk about time and space. Means how much amount of time our algorithm is going to consume and how much memory it is going to consume. So both the things are important, but when it comes to the selection of either of them, then we consider one of them as the most important factor during the calculation of efficiency of an algorithm. So what are these factors? So these factors are the time, which is the CPU time required to execute an algorithm, and the second one is the space, which is the amount of memory used by the algorithm for its execution. The lesser resources an algorithm consumes, the more efficient it is. That is, if an algorithm consumes minimum time as well as lesser amount of space in the memory, then it will be considered as the most efficient algorithm. So here we have the time and space complexity, rather we call it as time and space trade-off. So it refers to a situation where you can reduce the use of memory at the cost of slower program execution, or reduce the runtime at the cost of increased memory usage. This means we can give priority either to time or to space, whichever suits our algorithm. But one thing we must remember, that memory is extensible but time is not. Hence, time considerations generally override the memory considerations. This means we have always to give priority to the time rather the space. So later on we will come to know, or we will explain about the time and space complexity in terms of the big O notations. So let us have a closer look on the asymptotic notations. So what are asymptotic notations? The word asymptotic means approaching a value or a curve which is arbitrarily closure. What do you mean by closure? Means we would try to maximize, or better to say, we would try to get accurate results by the help of asymptotic notation. It clearly measures the graph of an algorithm, the growth of an algorithm in terms of three different major complexity levels or asymptotic notations. We have the different asymptotic notations, like we have theta notations, we have omega notations, we have big O notations. So all the three notations work differently. But one thing is common, that all of them measures the complexity levels, the efficiency, the growth of an algorithm in three different ways. Now these asymptotic notations are used to analyze the complexity of any algorithm in terms of time and space. So just now we have discussed the time and space trade-off. So the asymptotic notations are the mathematical tools to represent time complexity of algorithms. And the main idea of asymptotic notation is to have a measure of efficiency for a given algorithm. So we will just look briefly about these asymptotic notations and how to calculate these complexities. So here the first thing is the theta notation. A theta notation defines exact asymptotic behavior it bounds a function from both the upper as well as the lower bound. What does the upper and lower bound means? The upper and lower bound signifies the maximum growth as well as the minimum growth for a given algorithm with respect to a given time interval and a given number of elements or problem size. Since it considers both the upper as well as the lower bound, it is used for analyzing the average case complexity level of an algorithm. Average case means upper bound plus lower bound upon 2. That is the average. It does not give upper bound plus lower bound upon 2, but nearly it calculates the average case complexity. So during the calculation, we drop the lower order terms and ignore the leading constants. Leading constants means suppose we have n as a number which is being multiplied by 3, that is 3n. Then we will try to remove or omit this constant, that is 3, from the given equation. So we will calculate all these things, we will see. So let us consider a function g of n, then its theta of g of n will be given by a relation as, so here theta of g of n is equal to f of n, where there exist positive constants. We have discussed the positive constants c1, c2 and n0. Here this c1 and c2 are the two constants that represents the lower bound and the upper bound of a given algorithm, and the n0 defines a situation, a position where we consider both these cases, that is the upper and lower bound, nearly equal. That is arbitrary closure. Now, so theta of g of n is given by f of n, where there exist a positive constant c1, c2 and n0 such that the function f of n lies between g of n multiplied by first constant and g of n multiplied by second constant, such that it is always greater than or equal to 0 for all values of n which is also greater than equal to n0. That is the closure point. Hence, the function f of n belongs to the set theta of g of n if there exist positive constants c1 and c2 such that it can be mixed between the first constant with g of n and the second constant with g of n for sufficiently large numbers of n. That is the input size. Hence, if a function f of n lies anywhere in between g of n with constant c1 and g of n with constant c2 for all values of n greater than equal to n0, then the function f of n is said to be asymptotically tightly bound. That is, the graph will always lie in between the lower and the upper bound. This one, the purple one, signifies the average case efficiency, which is given by the theta notation. The next one, we have the omega notation. So here the theta notation gave us the average case efficiency. Similar to this theta notation, the omega notation will consider one of the bound. So which one will be considered by omega notation? This omega notation considers the lower bound of the running time of an algorithm. Since it considers the lower bound, it gives the best case efficiency of an algorithm. And similarly, if we try to calculate it in terms of g of n, then the omega of g of n will be given by f of n, where they exist positive constants c1 and n0. Positive constants c and n0, where n0 is a point which provides a closure point between the both graphs, and c is a constant which is used within in the graph for calculation. Hence, so omega of g of n is given by f of n, where there exist positive constants c1 and n0 such that the g of n, when multiplied by a given constant c, is always greater than 0 and less than f of n, that less than equal to f of n for all the values of n, which is always greater than or equal to the arbitrarily closure point, which is n0. Hence, the function f of n belongs to the set of omega g of n if there exists a positive constant c such that it lies above the g of n multiplied by the given constant for sufficiently large numbers of input size n. Hence, for any value of n, the minimum time required by an algorithm is given by omega of g of n. Okay, so we have seen the theta notation, we have seen the omega notation. Now the big O notation. The theta notation gave us the average case efficiency. The omega notation gave us the best case efficiency. Now remains the worst case efficiency. So the algorithmic implementations mostly focus on measuring the worst case efficiency. Hence, nowadays the big O notation is considered as the widely used asymptotic notation to calculate or to measure the efficiency levels of the algorithms. So what is big O notation? So big O notation represents the upper bound of the running time of an algorithm. Since it represents the upper bound, it is widely used and it gives the worst case complexity of an algorithm. The calculation goes similar. So for any given function g of n, here I missed one thing. It will be big O. So for a function g of n, the big O g of n will be given by the similar relation, that is f of n, where there exist positive constants c1, c and n0 such that the f of n will always lie between 0 and g of n multiplied by the given constant for all the values of n which are greater than equal to n0. Hence, the function f of n belongs to the set omega big O of g of n if and only if there exists a positive constant c such that it lies between 0 and g of n multiplied by the given constant for sufficiently large value of the input size n. Hence, the graph for the big O notation will fall slightly to the actual graph, which is given by a constant multiplied by the function g of n. Okay, moving further. So here we have the methods for determining the efficiency. So what are the things that we must consider? So to measure the efficiency of an algorithm, you can write programs based on the algorithm. Then execute it and measure the time it takes to run. So the programs which we write does not take much time. Within fraction of second it gets compiled. So for this we need to have a broader, not broader program, but the programs which have more LOCs, that is lines of code, which engages or makes the compiler busy in decoding those instructions which we had given in the form of a program. Then the execution time that we measure in this case would completely depend on a number of factors that we have already discussed. That is the speed of the machine. Some computers are faster, some are slower. So the people who are using faster machines will have maximum efficiency. The people who are using slow machines or legacy machines will have higher level of complexities. Similarly, the compiler will also play a vital role. The operating system, the selection of programming language, and the most important thing, the size of input supplied to the program. However, we would like to determine how the execution time is affected by the nature of the algorithm. So here we will look at some points. So the execution time of an algorithm is directly proportional to the number of key comparisons involved in the algorithm and is a function of n, where n is the size of input data. So just now we have seen in all the three complexity level asymptotic notations, the n was the size of input. Here also we will consider some graph associated with the big O notations which will measure the efficiency or the complexity level for a given graph in terms of time and space complexity or trade-off. So the rate at which the running time of an algorithm increases as a result of the increase in volume of input data is called the growth of the given algorithm. Means, suppose the x-axis is giving us the detail about the input size, and y-axis is giving us the detail about the time utilized, time consumed in processing the given input. Then the graph will be given, or the growth of the graph will be given by the processing of data and the time consumed by any algorithm. Hence, the order of growth of an algorithm is defined by using the big O notation. It is also sometimes known as big O, OH, big O notation. And this big O notation has been accepted as a fundamental technique for describing the efficiency of an algorithm. Here we have some growth levels for the algorithms. So we have the constant, the logarithmic, linear, log linear, quadratic, cubic, and exponential growth levels. Let us look at them one by one. So here, according to the order of growth, the big notations can be arranged in an increasing order as, so we have the growth levels in increasing order, that is, the first one is big O1, that is the constant graph, then the big O log n, that is the logarithmic, then we have the linear, then the log linear, then quadratic, then we have cubic, and then we have exponential graphs or exponential growths. So let us look them one by one. The first one here, which we have picked, this graph provides the problem size in terms of n, that is in the x-axis, and we have the execution time in y-axis given by t. So this graph denotes a straight line parallel to the input size axis, that is parallel to the x-axis, which signifies that for any number of inputs applied to the algorithm, the time required to process all the given input is constant. Whether it is 1, 2, 3, 4, whatever milliseconds or seconds, it will remain so. That is, the big O1 provides a constant growth of an algorithm, which are generally used in case of real-time machines, real-time algorithms. That is, the given time is fixed, and in those fixed number of time, the algorithm is capable of processing any number of inputs. The second one, we have the logarithmic graph. As we can see that this graph goes on slightly going to be parallel to the problem size, that is parallel to the x-axis at a given point of time. That is, after consumption of a given time interval, this graph will be parallel to the x-axis, that is the problem size axis. Means the growth of this graph is towards a constant graph. That is, it provides better efficiency as compared to the other growth, but it is lesser than the constant graph because it tends to be a constant, while a constant graph remains constant. The third one we have is the linear graph. Linear graph means 45-degree graph. As we can see here, when the problem size increases, the time required to process those input gradually increases, which means the problem size and time are directly proportional to each other. That is, whenever the problem increases, the time required to process the problem also increases. The next one we have is the log linear, which tends to be parallel to the time axis at a given point of time, which is much more farer. That is, after a long time, this graph will give us the worst case efficiency. That is, when a problem size increases to huge amount, then there will be a time when the algorithm will not be able to process all those given inputs, as it requires night time to process those inputs, because this graph at some point of time will be parallel to the time axis. The next one we have is the quadratic, that is the time required to process the input size will gradually increase with the power of 2, and soon it will acquire the infinite time level. Then we have the next one as the cubic graph, which is an extension to the quadratic graph. It will be closure, or it will be parallel to the time axis in much more closure time as compared to the other graphs, that is the quadratic graphs. And similarly, the worst one, that is the big O, 2 to the power n, that is the exponential growth. This exponential growth provides the worst case, that is when a problem size increases to a minor extent, the time to process those minor input increase will be much more higher as compared to the other algorithms. Hence, it gives the worst case efficiency. So these were the few algorithmic notations, rather known as the asymptotic notations. So we will come back again when we will discuss about the different data structures. So in the next session, we would discuss the topic linked list. Thank you so much.